So yesterday we stopped with this summary on the experimental techniques which can be used to elaborate some chemical kinetic reaction mechanism, shock tubes and rapid combustion machines, which can provide both um, global and detailed information. Flow reactor, which mostly provide detailed information in terms of reaction of concentration of species as a function of different parameters such as time, temperature, or pressure, and flames, which provide both global and detailed information. So now we will look at the modeling aspect of combustion chemistry. So to perform chemical kinetic modeling, we need accurate kinetics, accurate thermochemistry, and transport data. We can use theory and measurements, also estimations or tabulations for these. And finally, we need accurate data that are used to constrain the model. And this data can be obtained using the techniques that we presented yesterday. So for the kinetic modeling, most of the people are using the Kenkin computer package. A kinetic reaction mechanism with modified Arrhenius equation that is shown here are included in the reaction mechanism, and these are taking into account the effect of pressure and temperature on these rate constants. Reaction mechanism is with strong hierarchical structure developed. The core mechanism being that of hydrogen-oxygen, and it includes reactions involving H atoms, O atom, OH radical, HO2 radical, H2O2, molecular oxygen, ozone, and molecular hydrogen. And when we are dealing with hydrocarbons or oxygenates, we start with the core mechanism, then we have the CO2 submechanism, the formaldehyde methanol submechanism, methane and ethane mechanism, ethylene acetylene, C3, C4, C6, and up to at least the size of the fuel we are burning. So of course, there are strong interactions between these different sub-mechanisms, and this is generally taken into account. Over the years, the size of mechanisms which have been developed has increased a lot. And you can see on this graph taken from the review paper in Progress on in Combustion Science, that for methane, we are about here with a number of reactions of about 200, and about 40 species. But when we are speaking of large methyl esters, we are now with about 10,000 reactions and several thousand species. Although here NOx chemistry is not included. If we were using, if we were adding NOx chemistry, you would get about 100 additional reactions. So this is an example of a kinetic reaction mechanism for the C plus fuel, hydrogen. And you can see here how it is organized in the file that is processed by Chemkin. We provide the reaction with reactants, M being a collider, divided by either the equal sign or an arrow or double arrow, and the products on the right hand side. Then here we have the pre-exponential factor in the Arrhenius equation, this one. Then we have the exponent of T and the activation energy. Exponent of T, activation energy. And then we can put some comments. So these are the common reactions used for the core mechanism, hydrogen oxidation. Among these reactions, some of them are of particular importance, as I told you before. This is the main branching reaction, H plus O2, H plus O, and H plus O2 plus M giving HO2, which is competing with the previous one. We provide thermochemistry in the NESA format. So it's a polynomial representation of the heat capacity and enthalpy, entropy. And with this thermochemistry and the forward rate constant, which is given here, you can compute the backward rate constant using the equivalent constant, which is equal to forward rate constant divided by backward rate constant. This is organized in two polynomials. The first one is for the high temperature range from here 1000 to 5000 K, and the first and the second polynomial is for the lower temperature range from room temperature to 1000 K. Well, it can be a different value. Here it's always 1000, and also the upper temperature can be different from the value which is used here. Transport data are also provided. This is not always used, but if you are using if you are computing flames, of course you need these. So there are different parameters which are provided. So first of all, the species, then a number which indicate if the species is an atom, then you have a 0. If it's a linear species, then you have a 1. And if it's a non-linear species, it's 2. The Lennard-Jones potential well is also provided. Lennard-Jones collision diameter, dipole moment, polarizability, and rotational relaxation collision number are provided. So this is documented in this report from somebody. The rate constants that are used in these mechanisms can be obtained in papers where they have been measured. in review papers, in tabulations, databases online, for example, the NIST database. And I will give you an example of the way these rate constants can be measured. It's a simple case. It's a reaction of OH with a fuel. Here it's we have two fuels. For first the dimethyl ether, and then I will show you another example with neopentane. So OH radicals are produced by photolysis of water, for example, and monitored by fluorescence after OH have been pumped by light, either a laser or by a resonance lamp. At low radical concentration, the OH fluorescence is directly proportional to the OH concentration, and the first order rate expression can be integrated to obtain through this equation, you will obtain the decay of the fluorescence with time. So K first is the total first order decay rate. K0 is the first order rate constant for OH removal by other processes than the reaction of OH with the reactant, here dimethyl ether. So it can be a reaction with some impurities or diffusion out of the viewing zone. And Kr here is the bimolecular rate constant that you want to measure for the reaction of OH with the reactant. So this is an example of an experimental setup. This one was built at Sandia. So the reactor itself is here. You fill the reactor. You feed the reactor with the mixture of the fuel and eventually possibly water, if you want to use water to initiate OH radicals. You have an excimer laser here for the photolysis of the precursor of OH. And here you have another laser which will excite OH radicals, and you will get fluorescence of these radicals recorded on the photomultiplier here. And then you will get this kind of signal, the exponential decay with time. So value of the K first are determined from various reactant concentration by nonlinear least square exponential analysis for the exponential OH fluorescence decay, ranging from about 20 microseconds to about 2000 years. And then you will be able to plot this kind of graph, K first minus the K0, which is the loss of OH in other processes, as a function of fuel or reactant concentration, where here it's plotted in millitole. And then the slope of this line will give you the rate constant. These experiments are repeated at several temperatures to obtain the variation of the rate constant and function of temperature. This is another example of the same plot. So K first minus K0, or K first only, here it's K first only, as a function of the concentration of the reactant. So for the modeling, we consider the temperature dependencies of elementary reaction. So it goes back to 1889, where Arrhenius proposed the so-called Arrhenius equation from direct observation of the plots of rate constant versus temperature. And he showed that over a small range of temperature, the rate constant varies exponentially with temperature. But later, we figured out that when we are considering a larger range of temperature, this equation doesn't really apply, and you need a correction, which is introduced here as a power of temperature. And clearly you can see here that we don't have a straight line over the temperatures. You can have a straight line over certain range, but not over the entire range of temperature. There is a curvature here which appears. This is also a very important reaction in combustion, the oxidation of CO by OH. And this is almost the only oxidation route for CO in combustion. Reaction with O atoms is very slow, and that with HO2 is slow also. I will show you some examples of the variation of rate constants with temperature, and you will see that this initial equation by Arrhenius cannot apply in several cases. So this is the case for the reaction of HO2 with HO2, giving H2O2 plus O2. If you remember what I told you yesterday, this is a very important reaction above 800 K, because below that, HO2 are not very reactive, they accumulate. They proceed through self-reaction, and H2O2 accumulates, and above 800 Kelvin, H2O2 starts to decompose and produce two OH radicals. So you can see that below about 800 Kelvin here, this reaction, this rate constant goes down, and then it's going up with a strong activation energy. Similarly, the reaction of OH with HO2 also doesn't have an Arrhenius behavior. There are some data here around, well, this is room temperature. Around room temperature, there is not much of temperature dependence, but above 1000 K, the temperature dependence starts to be strong. And besides that, the reaction can be pressure dependent. When you vary the pressure, you can get an increase of the rate constant, which doesn't fully follow a linear increase in the log scale representation here. So this line represents the low pressure rate constant, and this is the high pressure limit. So we call this one K0 and this one K infinity. So the rate constant actually behaves slightly differently, and this is what we call a fall-off behavior. This was initially described by the formalism of Lindemann and Hinchelwood, and later on there has been several improvements of that. This is another example of such behavior for the recombination of methyl radical colliding with argon to produce ethane. and the measurements were performed as a function of pressure and temperature. You have here the constant at 200K up to 1,600. So the first simple formalism is that of Lindemann and Michelwood. We assume every collision leads to stabilization. Here M is the collision partner. So the first reaction is A plus M, giving an intermediate excited A star. And A star plus M can give back A plus M, or it can decompose and produce products. The quasi-steady state approximation for A is then the derivative of the concentration of A star over time. And it is 0 when we consider we are at steady state. And we can write this equation: the concentration of A star is equal to K1 times A times M, the two reactants, divided by K2 times M, and plus K3. And the rate then is equal to K3 concentration of A star equal of K3 K1 A concentration of M concentration of A divided by K2 concentration of M plus K3, and this is what we call K unimolecular times concentration of A. So at very high pressure, at the high pressure limit, M tends to infinity. So K2M is much larger than K3. And this equation can be simplified. And then we get K unimolecular equal K1, K3 over K2. At the low pressure limit, this equation can be simplified also, because M is getting close to 0. So K2M is much lower than K3. Therefore, the rate it can be written as K1AM equal K0A, sorry, which means that K unimolecular is K1 times concentration of M. So this is somehow a rough approximation, and when we compare the experiments, the experimental results shown here with this Lindemann-Michelwood approximation, you can see that most of the time it overestimates the rate constant in the follow-up regime. Therefore, Troy proposed a more sophisticated description of this behavior by introducing several parameters which are described on this slide. And so this is I won't go into details, but this is implemented in Chemkin, and they are using the F, this factor, this correction factor with these three parameters: T triple star, T single star, and T double star, and this A factor here. And how is it implemented? So you write the equation as usual. You write the high pressure rate constant here, and then the low pressure rate constant, and the factors A, T triple star, T star, and well, here they didn't use the T double star, but it would be the force parameter to be introduced in ChemChem. So this allows to much better fit the experimental data than the simple Lindemann-Hinshelwood formalism. When you are performing chemical kinetic modeling, you can develop your own model, or you can use models available from the literature. But in both cases, you can be interested in knowing how a reaction proceed, and how reactants and intermediates are formed and consumed, how products are formed. So you can do that by performing a simple computation. So for a given reaction, you can compute its reaction rate and divide it by the sum of the reaction rates producing the product you are interested in, and this will give you the rate of production. The rate of consumption will be the rate of a given reaction divided by the sum of the reaction consuming product one. So then you can figure out what's the percentage, how important reaction one is compared to the others, and figure out what is the flux of species in the mechanism. And you can also compute the net rate of production, which is the total rate of production minus the total rate of consumption of a given species. And it tells you if at a given condition the species is still in the process of being formed, or if it's in the process of being consumed mostly. So I will show you an example of this. So this is here we studied the interaction between NO and propane. Well, I will present later this type of interaction where we can reduce nitric oxide by introducing hydrocarbons, and radicals generated by the oxidation of hydrocarbons can interact with NO and transform it through several steps to molecular nitrogen. So here we plotted the normalized NO rate of reaction as function of temperature, and we could figure out that there were reactions which were producing or consuming NO. So above zero, it's producing. Below zero, it's consuming. And you can see there is a kind of symmetry here. For example, reaction 70, which is CH2 plus NO giving HCN plus OH, is shows symmetrical normalized rate of reaction with this one, which is 65. And 65 is NO plus H, giving HNO plus N. When you look at the different at these different curves here, you figure out that one production is cancelled by one consumption. And finally, there is a reaction here, 94, which is not very important in terms of flux, chemical flux. But this fraction is not counterbalanced by another reaction. And this reaction is the reaction of HCCO plus NO, giving HCN plus CO2. There is another one which also consume NO. This is reaction 93, HCCO plus NO giving HCNO plus CO, but it is counterbalanced by the oxidation of this product here by O, giving back NO. So it cancels out. Well, so through this analysis, you can figure out that this is the key reaction responsible for the reduction of NO under these conditions. I quickly answer some of the questions I got. This is another example where we can figure out what are the reaction pathways and how the introduction of traces of ozone can strongly modify the oxidation rate of a given hydrocarbon. So this is here we are considering the oxidation of isoctane. So isoctane is PRF 100. It is not very reactive below 800 Kelvin. And here we plot the rate of consumption a function of time at 800 K. The initial pressure is 50 bar and the equivalence ratio is 0.3. And you can see here that there is not much of reaction below about 10 to minus 1 millisecond or 3 millisecond here. There is a slow oxidation going on with HO2, a bit with H atom, a bit with oxygen atom, and there should be also the reaction with OH. It's relatively slow. And once you introduce 10 ppm, 10 ppm is a very small quantity of ozone. What you can see is that the reaction of isooctane with O atom gets very important. It was just here, 10 to the minus 20, and then it jumps to 10 to the minus 5. And consequently, there is also a reaction of the fuel with OH, which was also in the range of 10 to the minus 17, maybe. So strong jump of these two reactions. And so this is due to the fact that when you have no ozone introduced, so the fuel has no other possibility initially than reacting with O2, producing HO2, which reacts with the fuel, produce a radical, which then will react with O2 or decompose by interaction with collider. When you put traces of ozone in the system, the fuel reacts readily with O atoms. O atoms abstract an H atom from the fuel, produce OH, and OH react with the fuel to produce a radical. So the action of this guy produces a very reactive species, which speeds up significantly the oxidation of the fuel. So this is shown here. So by this analysis, you can figure out how the reaction proceeds. And this is another example of the interaction between ozone and fuel. Here we are using a much simpler fuel. We are using methane. Methane is consumed by reaction with OH and O atom in absence of ozone, producing CH3. CH3 reacts with HO2, produces CH3O, which react with O2, producing formaldehyde and HO2. And formaldehyde reacts with OH and H to form HCO, which can react with O2 to produce HO2 on one side and CO on the other side, and CO is oxidized by OH to produce CO2. When ozone is present in the system, it will readily decompose and produce an O atom, so it will increase the fraction of oxygen atoms here, but you still produce CH3. CH3 are still oxidized by HO2 to produce CH3O, which react with O2, and the same way you get HO2. But O atoms can react also with CH3, which is new, and contribute to the formation of formaldehyde. The oxidation of formaldehyde, which was previously going through, which was due to the oxidation by OH and H, now can also formaldehyde can also be depleted by oxidation by oxidation or by O atoms producing HCl. And the overall effect is that there is a faster oxidation of methane by addition of ozone. One other thing we are interested in is how dependent on the model parameters, which can be the rate constant, for example, the A factor, or the enthalpy of reaction. How these parameters influence the response of the model. So if you modify a given rate constant, will change something in your simulation, or there will be no effect. Since these rate constants have some uncertainty, which can vary very much from one reaction to another, it's an important aspect that people who are doing modeling are interested in. So what is the impact of a variation of a given parameter on the model prediction? What reactions influence the prediction of the formation or consumption of a given product? So if we consider that rate constant are the parameter which is important, so we have an initial rate constant which leads to the formation of product 1 at this initial concentration. Then if you multiply the rate constant by a small factor, you will get a new concentration. And if you divide this rate constant by a small factor, you will get another answer. And the sensitivity will be the difference of these divided by the initial predicted concentration. And this will tells you how important are the kinetics here on the formation or consumption of a given species. So this is an example taken from the literature. They looked at the laminar burning velocity prediction for methane air flames at atmospheric pressure, initial temperature, room temperature. And so they varied the rate constants in the mechanism by a factor of 5, which is huge. And then they computed this sensitivity coefficient for all these reactions. And what they figure out is that the reaction H plus O2 giving you H plus O is the most influential reaction. It has the highest sensitivity. It is followed by the reaction of oxidation of carbon monoxide reacting with OH, producing H atoms. So if you remember what I told you in previous lectures, I told you that laminar flame speed is very much influenced by the flux of H atoms. And you can see here that this reaction is involving H atom, and it is very sensitive. This one is also involving H atom. It is very sensitive. This one is involving H atom, and that one also. And that one, which is less sensitive, is also involving H atom. So we can compute these sensitivity coefficient by simply varying the A factor, the pre-exponential factor. We can also look at the impact of varying thermochemistry on the computations. These are things that people are doing when they want to figure out what is influencing their computational results. And especially when you have some difficulties to match some experimental concentration profile or flame speed or ignition delays. So this is another example of the use of sensitivity analysis to figure out if when you vary significantly the equivalence ratio is all the the sensitive or influential reactions the same, or are they different? And we can clearly see here that under fuel very lean conditions, these two reactions, C2H5CO plus O2 and C2H5CO giving C2H5 plus CO are the most influential, whereas it's not the case at all under fuel very rich conditions where these two reactions are, or three reactions here, in this one, are more important are much more influential under fuel rich conditions than under fuel lean conditions. And this is very useful because sometimes when you are simulating experiments over a range of equivalence ratio, your model fits very well the data at maybe the fuel-rich conditions, but under lean conditions, it doesn't work very well. And then you can figure out that there are reactions which are not influential in one condition, very influential in the other conditions. And then you can have a look at their rate constants and see if within the uncertainty attached to these coefficients, you can slightly or move in one or the other direction in order to better fit the data. This is the way to proceed. I'll stop here and I try to answer the questions which I got. So the first question, I don't think it's relevant to what I said so far. Second question, for third body reaction in chemkin where high and low pressure rate coefficients are given, what pressures are considered high and low? So in the chemkin files, you can introduce this I can go back. Yeah, here. So what you are providing is the high pressure limit K infinity and the low pressure limit K0 and the Troy parameters. You can also provide the Lindemann-Sherwood parameter the same way. what is the high pressure limit? Well, it will depend on reactions. So there is no general answer depending on the reactants. The reaction will reach its high pressure limit at different pressure than another reaction. So this schematic here shows you the evolution, but it's just a general graph. But for a given reaction, maybe this rate will go like this, and then you will have a different fall-off. Interesting question. For a simulation of a diesel engine, should I use high temperature mechanism or combination of high and low merge mechanism? Yeah, you need to consider both because ignition starts with low temperature chemistry. Okay, so let's get back in about 5 minutes to continue. Okay, we continue with the modeling aspect and pressure temperature dependencies of reaction pathways. So this is the well-known explosion limit of hydrogen and oxygen mixtures. And if we look at this graph, for example, we look at what's going on at 800 Kelvin. So at low pressure, the reaction of oxidation is very slow. And when we increase the pressure, suddenly we switch to a very reactive domain, which we call the first explosion limit. We continue to increase the pressure, and then we reach a new domain where the reaction is getting slow again. Increase the pressure still, and reach a third limit where the reactions become very fast again. So we didn't change the reacting mixture. We stayed at a given temperature. We only changed the pressure, and we can see that the behavior is changing from slow reaction to fast reaction to slow reaction to fast reaction. So what's going on? That clearly cannot be explained by 2H2 plus O2 giving 2H2O. This must have to do with some of the reactions, elementary reactions, which constitute the reaction mechanism of hydrogen oxidation. So at low pressure, so we still work here. At low pressure, the only reaction usually that can be responsible for the oxidation of hydrogen is reaction with O2. It's a slow reaction, which produces two radicals, HO2, which, believe me, are not very reactive, and H atoms, which are very reactive. But because diffusion is very easy at this low pressure, you can have recombination of H atom, which can occur in the gas phase, but also on the surface of the vessel, and reform H2. Therefore, there is no acceleration of the reaction. But when the pressure gets high enough, diffusion of H atom become slower, and then they can survive longer and react with molecular oxygen with this main branch, through this main branching reaction, producing OH radicals and O atoms. And then the reaction is, the overall consumption of hydrogen gets very fast. And this goes on over a range of pressure, like this. And then gradually there is another reaction of H plus O2 that I mentioned before, which produces HO2, which becomes important and increasingly important when pressure increases. And then it's competing with this reaction, which becomes less important. And then the reaction, the overall rate of oxidation of hydrogen starts to decline. HO2 are not very reactive. They accumulate, they can react with themselves and produce H2O2. Continue to increase the pressure, and then this amount of H2O2 is high enough to decompose and produce OH radicals, which will initiate the reaction of oxidation of the fuel, and then we reach the third explosion limit, and the reaction gets very fast again. So you can see that with this very simple system, H2 plus O2, you can observe somehow strange behavior, moving from slow reaction to fast reaction to slow reaction to fast reactions. So what happens with this very simple system can also occur with more complex systems, and I will show you that later. So if we go back to the reaction mechanism, we have two reactions which are responsible for the acceleration of the oxidation of hydrogen. This reaction, H plus O2 giving OH plus O, and the decomposition of H2O2 giving 2OH. And the reactions which are responsible for the slowdown of the reaction are the recombination of H atoms to reform molecular hydrogen, and the recombination of H atoms with O2, forming HO2. And the transition, the first transition is due to the fact that HO2 react with themselves and produce H2O2 here. Again, when the concentration of H2O2 is high enough and pressure high enough, then we have decomposition, and the reaction starts to be fast again. So I've shown this graph before. The concentration of the fuel, the variation of the concentration of the fuel as a function of temperature. So you oxidize the fuel, you get consumption here over the temperature range 500 to about 650, and then the consumption start to decline, and you almost get back to the initial conditions until you reach about 800 K, where the oxidation starts again. So this is a behavior which is also due to change in the mechanism in the competing reactions. So here in this range we have the cool flame. Here we have what we call the negative temperature coefficient. Negative temperature coefficient because when you increase the temperature, it has a negative effect on the overall rate of oxidation of the fuel. And then you have the transition to high temperature. In the literature, you can also get this kind of graph where people were able to observe several cool flames as function of pressure and temperature. Here it's the case of normal propane. And if we were plotting if we were moving at a given temperature, if we were moving to higher pressure, we would go from slow combustion regime here to a cool flame regime and transition to hot ignition, which would be high speed oxidation of the fuel. So this is for propane, and this is another example with another fuel, but similar behavior where you change from you have different regimes when at a given temperature you move to higher pressures. So pressure and temperature have a significant effect on the reactivity of the systems. So this is a very simple representation of the oxidation of a given fuel. So we start with a fuel here. Let's say it's an alkane, like normal ethane. So we have oxidation of this fuel by H-atom abstraction. This abstraction most likely will occur through reaction with OH radicals. And these OH radicals will form a H2O and produce a radical here, an alkyl radical. This alkyl radical can react with molecular oxygen, produce a peroxy radical. And this peroxy radical can isomerize by internal H-atom transfer. If you start to write this radical, for example, well, I will do it simple. So here you have one oxygen, second oxygen, and here you have an H-atom. So this H-atom can be transferred here. And this is what we get, QOH. And then here on this carbon now, you can add oxygen again, and you get this guy. You can have a second H-atom transfer and get this new species, which can decompose produce OH radicals. And if you recall here, we said that it's most likely with OH that reaction proceeds. So here you form OH again, and this ketohydroperoxide here. So it's a ketohydroperoxide that we have here. It can decompose and produce another OH atom. So we started with a reaction consuming one OH, and at the end, we produce two OH radicals, which explains why the reaction of oxidation gets faster and faster here. Once you are approaching 600 Kelvin or so, some of the intermediates here are not stable. And as soon as they are formed, they go back to the reactants. And therefore, there is less and less possibility to form a large amount of OH radicals. And as a result, the reaction slows down, and you almost do not consume any fuel. When the temperature continues to increase, these channels disappear, and you are mostly forming one OH through the formation of a cyclic ether, or the decomposition of this QOH to form olefin carbonyl and OH. So only one OH on both sides. At higher temperatures still, this almost totally disappeared, and the formation of RO2 is getting less and less important. And then you have two channels which are getting important. Reaction of the alkyl radical with O2. It reacts by H atom abstraction. So O2 abstract an H atom here, and then it will produce an olefin and HO2. And also at higher temperature, we can have the decomposition of this radical to form an olefin and another radical. And at even higher temperature, because the H bond are stronger, you can get an olefin and an H atom. So you can see that from this simple scheme, you see how the reaction pathways are modified by temperature. If we take dimethyl ether as an example, dimethyl ether will react with OH radicals. Since it is a symmetrical molecule, either you abstract from this methyl group or this methyl group, doesn't matter. You always get the CH3O CH2, which can be peroxidized by addition of O2, and then you get this guy. By H atom abstraction on the methyl here, you get CH2O CH2OH. You can add oxygen on this carbon, and you get this radical, O2 CH2O CH2OH, which can decompose by on the peroxy hydroperoxy group here, you can break this bond between the two oxygen. It's a weak bond, and you get an OH radical. Plus this guy here, and this guy can also decompose and produce an OH radical, and the decomposition of this guy will form CH2O plus OCHO. When the temperature gets above around 600 K, so all these channels will disappear. And this first hydroperoxy radical here will decompose, produce two formaldehyde molecules and an OH radical. And if you increase the temperature still, the formation of the initial peroxy radical will almost disappear, and there will be decomposition of the first radical CH3O CH2 to form formaldehyde and methyl radical. So this is similar to what we presented for the other fuel, or for the generic case here. So when you are modeling a chemical system, we have branching reaction, which correspond to multiplication of the number of active species. So we've seen that at low temperature, it goes through the formation of a peroxy radical that can isomerize and form this species here after a second addition of O2. And then we can have decomposition and formation of OH radicals. At this stage, we can have also a formation of an OH radical by decomposition. At medium temperature, the reaction of H plus O2 giving HO2 is important. And then you consume a very reactive species to form a much less reactive species. But these less reactive species can still react with the fuel, for example, to form H2O2. H2O2 will accumulate until about 800 Kelvin, temperature at which it starts to decompose and produce two OH radicals. And in parallel to this reaction, we have also the self-reactions of HO2 giving H2O2. And at high temperature, this high temperature oxidation is dominated by this main branching reaction, the reaction of H atoms with the molecular oxygen producing two reactive species, OH radicals and O atoms. So this is a very simple representation of this chemistry, but I think it tells you quickly how it goes. Beside the reactions which are presented here, there are other channels which can be important. I didn't mention the possibility of peroxy radicals to react with themselves and produce two alkoxy radicals. These alkoxy radicals can then react through two pathways. Either they react with O2 and form HO2 plus an aldehyde, or they decompose and they will form an H atom plus an aldehyde. And RO2 can also react with other species like the fuel or formaldehyde or other species from which they can abstract an H atom to produce ROH, hydroperoxy radical. They can react with HO2 also to produce this ROH. And ROH can decompose and produce OH plus alkoxy, so the same products as on the this side. There is another route which is not written here. So beside the fact that they can produce RO plus RO, this reaction can also produce R O O R, an organic peroxide, which can in turn decompose and produce those gases. So the relative importance of all these channels is varying depending on the structure of the R group here, depending on the temperature, depending on the initial concentration. So it's a bit more complicated than it could seem from this scheme here. So I said beside this chemistry, there are other reaction pathways that can occur. One of them is the Korschek mechanism, which was initially proposed by Korschek and co-workers working at Ford Motor Company. And they were interested in the oxidation of lubricants in the liquid phase. And they figure out that these molecules were oxidized and producing carboxylic acid and other carbonyl group like ketones. But at that time, they were not really able to figure out how the reaction goes. And it has been proposed recently based on ab initio calculations that the reaction proceeds this way. So it's only for gamma keto hydroperoxide. So gamma means compared to the, based on the position of the hydroperoxy group. So this is the alpha carbon, the beta carbon, and the gamma carbon. So we have a H atom transfer to the carbonyl here, and then you have a subsequent bonding of this oxygen with this carbon, and then decomposition of this cyclic intermediate to produce a ketone here and a carboxylic acid. What's the effect of this kind of reaction? With it will slow down the oxidation of the fuel, because you add this ketohydroperoxide, which could decompose and produce OH. But here, it will, through this process, you have the formation of two stable species, an acid and a ketone. So the reaction will slow down overall. Another process which is also of interest, still it's interesting to note that this group from Professor Waddington at York University in Great Britain, they were also working on the oxidation of lubricants. And they figure out that there were processes involving double bonds and OH radicals. So OH radicals can add to double bond and produce this intermediate radical, which can react with molecular oxygen So molecular oxygen goes here, and you get this peroxy radical. Then the H atom from the OH group nearby can be transferred to this peroxy group and form a hydroperoxy group. And then here you have the formation of a double bond breaking, second formation of double bond, and here you break the bond, the weak bond between the two oxygen, and you form an OH radical plus an aldehyde and a second aldehyde here. So in this case, although you are forming two stable products, you reform the OH radical that initially started the process. So it's overall it's a propagation reaction, whereas here it's somehow a termination reaction. More recently, so these were proposed in the 70s. These were proposed in the 80s. And more recently, we figure out that there are other processes that can go on. So beside the fact that you have the addition of O2 on a radical to form a peroxy radical, which can isomerize and form this hydroperoxy species, hydroperoxy radical, which can add molecular oxygen and form this hydroperoxy radical. This guy can isomerize, but if the hydrogen which is transferred to the to this oxygen here is not the one where the OH group sits, then it will open a new channel, and there will be a possibility to have a third O2 addition and get this intermediate that can isomerize and produce these new intermediates that can decompose and form a ketodihydroperoxide product. But again, if the H atom transfer here is from a carbon without OH groups, there is a new open channel, and the reaction can go on this way. So through H atom abstraction, O2 addition, H atom transfer, O2 addition, H atom transfer, O2 addition, H atom transfer, until there is no possibility of H atom transfer on the structure. So we can get third products of third O2 addition, fourth O2 addition, fifth O2 addition, etc., depending on the size of the initial fuel. And this is what we saw for dipropyl ether. So beside the Korschek mechanism and the formation of ketohydroperoxides, we could see that there are more channels open and more chemistry, more complex chemistry going on. We also investigated the oxidation of larger fuels to figure out if these processes were occurring. On this scheme, I show the oxidation of limonene. Limonene is a terpene. Terpenes are natural products emitted by plants, by trees. This one is smelling lemon. And they have also been proposed to be used as dropping fuels because their energy content is relatively high. So there are some studies on terpene oxidation in the literature, in combustion journals, but there are many more papers dealing with terpenes oxidation in atmospheric chemistry journals. So in atmospheric chemistry, what people consider is that limonene will initially react by H-atom abstraction, will peroxidize, form this RO2 radical, which can react with itself, form this intermediate that can decompose, produce these alkoxy radicals, and then you have H-atom transfer, and you form this guy, which can react with O2, produce this species, which can decompose and produce this molecule, or it can also proceeds through H atom transfer plus O2 addition, form this one, which can decompose, produce OH radicals, or also proceeds through H shift, H atom transfer and O2 addition, produce this guy, which can decompose, forming OH, or which can react through H atom transfer followed by O2 addition. Then you get this intermediate that can either decompose or react through H atom transfer followed by O2 addition. And then you get something which is really highly oxygenated that can decompose and produce this species, which contains 10 atoms of oxygen. So this is what people dealing with atmospheric chemistry are considering. And it turns out that we observe also this chemistry under cool flame conditions, slightly below 600 Kelvin. The second channel is the one that I presented before. This is what I call here combustion channel. So you have the RO2, which are formed after H atom abstraction on limonene. Then you have H atom transfer. You form this alkyl hydroperoxide, which reacts with molecular oxygen, form this new peroxy radical, which can decompose, producing OH radicals and the keto hydroperoxide. You can have another H shift followed by O2 addition, producing this radical, which can also react through H shift and elimination of OH. You can have this species can also react by H shift and produce this species here with 3 hydroperoxy group. And you can have addition of O2 on top of it, and then it can decompose, or there can be further isomerization to get this intermediate, which reacts with O2, produces this radical that after H shift and elimination of OH form this keto with 4 hydroperoxy groups. But this radical can also proceed through H shift from a different CH group and form this species with 5 hydroperoxy groups, which can react with O2. Then you get this peroxy radical, and after H shift and elimination of OH, you get this keto product with 5 hydroperoxy group. So you can, and this is what we observed in our experiments. And this is something that was not much expected until recently. Well, of course, there are many other possibilities of reactions and direct interaction between these radicals, but these H atom transfer can be very efficient, very quick, compared to bimolecular reactions. So these channels exist under cool flame condition. Well, I won't start the next section of this lecture. I will answer questions before we have a break. Can you please? So the first question is: can you please add why the ignition delay time versus inverse temperature plot is called Arrhenius plot? Can we calculate the reaction rate or activation energy from this plot? Well, it's called, well, there are people who call them Arrhenius plot because it's, let's say, it's the same space, but it's just because well, it's convenient to present ignition delays as a function of the inverse of temperature. So is the presence of oxygen in ethers and similarly oxygenated species differ the oxidation pattern from alkane? So yes, yes, it does. The presence of the functional oxygen will weaken the CH bond nearby, at least on the alpha carbon, and then it will be easier to abstract this H atom, and the reactivity will be higher. This is the reason why when we consider this this plot here. So this plot is typical of hydrocarbons oxidation, but for ethers we would get something like this. It will be shifted here by maybe up to 100, between 50 and 100 Kelvin, towards lower temperature. I've seen in some papers that they represent rates in terms of Chebyshev polynomials. Could you please explain why this could be useful, different from Arrhenius behavior? Yeah, I can do that. So it's Chebyshev polynomials are used when the variation of the rate constant with temperature is more complex than what can be represented with a simple power of temperature. then they are using this representation. Does cool flame region depend on the reactant class, or just depends on the condition during the low temperature combustion, regardless of which class of reactants belongs to? Well, this is a similar question to what I had before regarding ethers and oxygenate. Yes, the class of reactants has an impact on the low temperature oxidation, and if there are chemical functions that weakens CH bonds, then the reactivity will appear at lower temperature. This is the case for ethers. This is the case for aldehydes, because the CH functional group is very easy to abstract. CHO, you abstract very easily the H of the CHO group, and then you have oxidation which starts at lower temperature. Yeah, this is the typical example. Okay, it looks like there is no more questions, so I propose we have a break now before we move to the next section of the presentation. So after presenting these rather complicated pathways, we will go back to something more simple. So first of all, this is the general mechanism of oxidation and pyrolysis of hydrocarbon, for example, for alkanes. After H atom abstraction, we get an alkyl radical, and we can have again a decomposition to form another alkyl radical, a further decomposition to get some a smaller alkyl radical or an H atom, and also directly from the fuel we can have decomposition to form some of these. This is represented here in the case of a normal octane. So you start with a C8 alkane that react with a radical which will abstract an H atom from the carbon chain. So there are 4 different positions. Position 1 here, position 2, position 3, 4, and this one, the next one, which could be position 5, is in fact position 1, 2, 3, 4. Okay, so we have 4 different carbon. So 4 different radicals, 4 different octyl radicals which can be formed, and each of them can react through pyrolysis to form different products. So the first one can react by beta scission to form ethylene, and ethylene plus different radicals. The first one here, which can in turn decompose and produce propylene, and a C3 radical. Here we can have a decomposition to form ethylene again, and a smaller radical with 4 carbon atom, butyl radical. And from this one, we can have formation of two different olefins and two different alkyl radicals. Oh, so what I didn't mention here is that there can be isomerization of this um, one exyl radical, which can isomerize two exyl or three exyl. So already starting from one alkyl radical from the fuel, you get a range of products here. If we go to the second radical in position 4, you can get two different olefins and two different alkyl radical. So propyl radical and ethyl radical. And from the 2-octyl, by beta scission, you can get propylene plus this pentyl, one pentyl radical, which can also isomerize and form a 2-pentyl radical. So both of them can decompose and form different product, ethylene here, and one propyl radical, or propylene and ethyl radical. And finally, the last radical in position 3 can decompose and form methyl radical. So it goes this way, methyl radical plus eptene, sorry, and it can also form butene plus butyl radical. So radical in position 1 mostly produces ethylene. The radical in position 2 mostly produces propylene. And the radical in position 3 will produce mostly butene and heptane. I'm sorry, there is a mistake here, it's heptane. And the radical in position 4 will produce pentene and exyl. And you can see that these different radicals can also react through isomerization, internal H atom transfer. So this is a scheme only for the pyrolysis of a simple, relatively simple normal alkane. And it shows the large variety of products that we can observe. So now you can imagine that if you are adding oxygen to the system, there are many more channels that will appear. One of the factors which influence both the products formation and the rate of reaction are the strength of the bonds. So typically in alkanes, the bond dissociation energy is up to 90 kcal per mole. CH bonds are the CH bond energy are higher, at least around 100 kcal per mole. And if we are thinking about the bond between the aromatic ring and H atom, it's even higher. Whereas in the benzene group, this bond is lower because of electron delocalization once you form the radical. And now if we have a look at the bond energy, bond dissociation energy, and the activation energy of some of the processes here, decomposition of methane giving CH3NH, you can see that it's in the same range. Similarly for the decomposition of ethane and decomposition of propane. Now I would like to spend some time discussing the effect of multi-fuel components on the reactivity, on the overall reactivity. And the first on this first graph, I show experimental results. Well, there is also a representation of the modeling result. The lines are from a model, kinetic model. This is the oxidation of methane and natural gas-like mixtures. These were performed in a jet stream reactor at atmospheric pressure. The resonance time of 140 milliseconds. And what we can see is that methane doesn't react under this condition below 1240 Kelvin, whereas the other mixtures react in the range of 1300, about 1300 to I'm sorry, 1130 and 1170. So it's way below. And why that? Well, in the case of methane, the only possibility is to have the abstraction or bond breaking of CH bonds, which are stronger than CC bonds. And in the case of all the other fuel mixtures, you have CC bonds, which are available for breaking, and also CH bonds. And therefore, the reactivity appears at a lower temperature. Also, there are possibilities to have many more H-atom abstraction options with CH bonds which are easier, with CH bonds which are lower, especially in the case of a C3 or a C4, which are C4 species which are present in natural gas. So that explains the fact that there is a strong, big difference between the reactivity of methane compared to that of these mixtures. Also, once you are able to get ethane or propane to react, there will be radicals produced, and these radicals will participate to the oxidation of methane. So the the reactivity, the overall reactivity will be higher. What I didn't mention is that the plot here, it's for methane mole fraction. This is the same component that we plot here. So much higher reactivity when you have the presence of species, of more reactive species. And what I didn't mention also here is that these what we can call additives are at much lower concentration. It's 10% of the fuel mixture. So now if we consider the different pathways of oxidation of methane that we can write. So methane, we start to react by H atom abstraction here. Form a methyl radical, and this methyl radical has two options. Either it is oxidized, either it reacts through a self-reaction to produce a C2 species. So let's look first at the C1 branch. So methyl radical can be oxidized by reaction with molecular oxygen or radicals, and they form formaldehyde. And formaldehyde by oxidation will form formyl radical. Formyl radical can either oxidize or decompose by thermally decompose and produce CO, and CO is oxidized mostly by OH radicals to produce CO2. And then we have converted the fuel into the final product, CO2. On the other hand, if we recombine methyl radical and produce ethane, C2 species, then we have a different behavior. Ethane will be also oxidized or consumed by H atom abstraction by OH radical O and H atoms, produce C2H5, and C2H5 can oxidize and produce acetaldehyde, which in turn can form CH3CO, and CH3CO can decompose and produce produce CH3 plus CO. But these ethyl radical can also either by reaction with O2 or decomposition produce ethylene, which is very important intermediate, and ethylene can react through different pathways. It can react through oxidation and produce simple radicals like CH3, CH2, and HCO. Of course, HCO that we saw here will also react by either thermal decomposition or reaction with O2 to produce CO. But ethylene can react through H-atom abstraction and form a vinyl radical. And these vinyl radicals are key intermediates here. And they can react with molecular oxygen and form this binoxy radical here, which can decompose and produce CO. But they can also react by thermal decomposition and form acetylene. And I think I told you before that acetylene is a key compound in molecular growth, which means the formation of aromatics, polyaromatics, and soot. It is also a very important species, and we will see that later, because it produces ketenyl radical HCCO, which can contribute to the reduction of NO. If you remember what I showed previously on NO interaction with hydrocarbons to transform NO into molecular nitrogen. These radicals are very important. So one of their formation pathway is through the oxidation of acetylene. So acetylene formed here can also react through H-atom abstraction, form C2H, and C2H can oxidize and form CO. But the other channel is the formation of CH2, which can oxidize and form both CO and CO2. CH2 can also produce CH by H-atom abstraction, and CH can react with O2 to form a CO. There is another channel because of the importance of methyl radicals. And methyl radicals, I didn't mention that, but methyl radicals are not very reactive radicals. And if they react with acetylene, they can produce C3 species like methylacetylene. Methylacetylene can isomerize into alene, and we can then produce propargyl radical C3H3, which by recombination with themselves produce benzene. And once you have benzene formed, then there is a possibility to grow further through a mechanism that I will present to you later, which involves acetylene. And this mechanism is called HCA. And then you can produce PAH, and these PAH can finally produce soot. So even if methane or natural gas overall are very clean fuels, there is the possibility to produce PAH and soot from their combustion, depending on the conditions. And what is very interesting is that you start with a C1 fuel, and finally you can get much bigger molecules here through this initial recombination of methyl radicals. And this is something which is not exceptional. There are many other systems where you are producing intermediately some radicals which are stable, and they tend to react with themselves and contribute to the growth of the molecules which are or the products. And this is what we observe here with methane. So this is this picture is the transition to the next part of this presentation, which will concern the formation of pollutant. So I will summarize what we went through so far. So to proceed with chemical kinetic modeling, we need accurate kinetics, thermochemistry, transport data. We will use inputs from theory, measurements, and also estimations of rate constant by analogy or tabulations. We need accurate data that are used to constrain the model, and this is really very important. Constraining the model. You don't want to write something that is not verified by experiments. Reaction mechanism. A reaction mechanism has a strong hierarchical structure, and the core mechanism is the hydrogen oxygen submechanism, which involves H atoms, oxygen atoms, OH radicals, HO2, H2O2, molecular oxygen, ozone, and molecular hydrogen. We've briefly seen that ozone can be a very strong oxidizer. We will see some other results later on, which shows that indeed it's a very strong oxidizer even at very low concentration. We've looked at temperature dependencies of elementary reactions, and we've seen that this behavior doesn't always follow the simple Arrhenius equation, even the modified Arrhenius equation. If you remember, there were some reactions where the rate constant was decreasing with temperature and then increasing. Pressure dependencies can be handled using a different approach. The simplest approach is the Lindemann-Sherwood approach, but it doesn't fit accurately the experimental results most of the time. The Troy approach is a much better approach to fit those. I also introduced some tools that can be used to understand what's going on and also to help improving the modeling. These include kinetic analysis through rate of productions and rate of consumption of products or intermediates. And clearly, you need to look carefully at these in order to figure out what's going on. And it can help figuring out that there are missing reactions, or some reactions which are included in the model are probably not forming the products they are supposed to form. Sensitivity analyses are totally complementary to these, and they will probe the response of the model to a variation, for example, of kinetic parameters, but it can be also the response to the variation of thermochemistry. Pressure and temperature dependencies and reaction pathways. I showed you that both have a strong effect on reaction pathways. The cool flame, particularly when you change the temperature from real low temperature, around 500, 550 K, and you increase it to 600, 650, you have a an increasing conversion of the fuel, and then when you reach a temperature around 600, 650, you start to have a slower conversion of the fuel, and this is due to reactions which proceed through different pathways, because some intermediate products become unstable thermally and decompose back to the reactants, and then do not oxidize further to produce particularly OH radicals. And also we've seen the transition between the cool flame, negative temperature coefficient, and the beginning of the high temperature oxidation, where H atom abstraction by O2 becomes important, decomposition of H2O2 becomes important, compared to much more important compared to what it was at lower temperatures. I also introduced the fact that we can observe the highly oxygenated molecules form in the cool flame regime, whereas these processes most of the time are ignored, whereas they are very important in the troposphere, and they will form, ultimately they will form some particulates, some aerosols, which are, well, this formation is a strong factor to global warming and air pollution in general. The oxidation, so this is what I summarize here. It's more complex than generally considered, and it's interesting to consider combustion chemistry and tropospheric chemistry, and I do believe that we can learn from, as combustion chemists, we can learn from what people are doing in the field of atmospheric chemistry, and also atmospheric chemists can learn from what we are doing in combustion chemistry. Regarding pyrolysis and high temperature oxidation, these processes are clearly less complicated or better known, although we've seen an example with methane, where the recombination of the methyl radical is responsible for the formation of C2 species, which in turn can react further by addition on a stable radical and produce some heavier compounds, such as aromatics, polyaromatics, and ultimately we can get soot. I briefly introduce the effect of small quantities of higher hydrocarbon to the oxidation of smaller or less reactive species. And what I told you is that the most reactive components drive the overall oxidation of the complex fuel. So this is true for natural gas, but this is true for other systems when you have the main fuel, which is relatively unreactive, and you add some other fuel, even at small quantities, which are more reactive, then you will get the overall fuel reactive. Another example could be the introduction of ethanol in mixture. Ethanol has very low tendency to oxidize in the cool flame region, in the low temperature, at low temperature. But if you mix this guy with long chain hydrocarbon or a methyl ester. Then the radicals, which will be produced through the oxidation of these larger molecules in the low temperature regime, will initiate the oxidation of ethanol. So this is something very general, and we must keep in mind that having very reactive species in a mixture will initiate the oxidation of the others. And when you are thinking about complex fuels like diesel fuels, you can you can imagine that these large molecules like hexaticane, which are very prone to produce cool flames, will produce radicals, and these radicals will be able to attack aromatics which are present in the fuel. So this is a very important aspect of the reactivity of complex fuels, and we will see that on Friday. Well, I've been a bit quick, and I could start the pollutants formation. We have still 20 minutes. Well, let's first look at the question. I have one question. In what stage does the effect of H2 enrichment on CH air conversion impact the increase in OH production and the reduction of CO and CO2? This is not so easy to answer, because it will depend, in fact, on the stoichiometry, on the occurrence ratio. If you are operating fuel-rich, the effect is different from what you could observe in fuel-lean conditions. So, but basically, the fact that you introduce hydrogen in a methane air mixture will speed up the oxidation of the fuel and increase OH production. Regarding the reduction of CO and CO2, I do not recall what's the effect on CO. I think that in fuel-rich conditions, in fact, you increase CO because you have H atoms which react with CO2, and there is a shift of the reaction CO2 plus H giving CO plus OH. So you can see it's not so simple because there are some equilibriums which are shifted by the introduction of H2, and I didn't push the button. I think that also it will depend on the quantity of hydrogen that you are mixing with methane. Small quantities will have less impact, and probably on CO and CO2 the impact can be much larger when you start to introduce large quantities of hydrogen. I'm not sure it answers fully your question, but it's not a simple. I cannot provide a simple answer. Any other question on what we saw today?
Hello, Professor. I have a question. Sorry, I'm not able to access the Q&A to write down my question, so I'll use my
Okay,
mic.
go ahead, please.
In the pyrolysis chemic reaction pathway that I discussed, it also leads to the formation of coke in fuel lines, which is only due to thermal breakdown of the fuel and in the absence of oxygen. So in the reaction mechanism of methane that you've shown, There is one pathway that leads to formation of acetylene in the absence of oxygen, and this can then undergo the Haka pathway to
Yes.
form
Yeah.
coke. So is the Haka mechanism the only mechanism that leads to formation of coke, or are there other mechanisms which are causing the formation of coke? And just to another follow-up to that is the flow parameters also affecting the formation of coke, and in what way?
Okay, so well, Haka is not the only mechanism which is responsible for the formation of this heavy material. Um, uh, we will tomorrow we will have a look at some of the mechanisms which are involved. Residence time, yes, residence time will have an impact. So slow flow will most likely uh, uh, be leads to a higher coke formation. But when we are speaking about deposits, this is something well, I didn't. I had no intention to speak about that, but I can briefly tell you that in nowadays, and it started well maybe 20 years ago. People were interested in understanding what the mechanism behind the deposits in tubing when near fuel injection. So there are different processes which are going on, and one of them is a low temperature oxidation of the fuel. So it's peroxidation, like the one I described today, and these processes can produce highly oxidized chemicals and hydroperoxy chemicals, and those can decompose and form some wax. And then this wax can evolve to coke if the temperature gets higher. So you see, really depending on the operating condition, there are different processes which are responsible for such deposits. The presence of oxygen in the fuel is a very important factor because when you heat the fuel, liquid state, oxidation reactions can start, form peroxides, and these peroxides can evolve towards the formation of polymers. These polymers, if you heat them further, they can get paralyzed and then form deposits. Does it answer your question?
Yes, Professor. Thank you.
Thank you. I have a Q&A over there. Okay, so. Any other questions? So if not, I can introduce what we will go through tomorrow. So tomorrow we will see what are the mechanism of formation of different pollutants and some ways to reduce them. And we will start with NOx, different formation pathways and ways to reduce NOx, either physically or chemically, and then we will have a look at ammonia, NO interaction, and some Also, we will have a look at sulfur chemistry a bit. It's funny chemistry. And reduction of NO by interaction with hydrocarbon linked to atmospheric chemistry again, because as I introduced it the first day, there are lots of connections between what's going on in the atmosphere and also in combustion. So even if the temperature is different, the concentrations are different, but some of the chemistry is similar at least. Yeah. So if there is no more question, I would like to say thank you for attending, and have a good afternoon, and we'll continue tomorrow.